Hi, I am Nuri Alam Tipu from the Department of Tripoli, BUIT, and today we're going to talk about a pretty basic topic of electrical engineering, the phasor diagram. Now, to understand a phasor diagram, first we have to understand what a phasor is. In electrical circuits, we always have to deal with sinusoidal signals of the form V equals Vm sine omega t, where Vm is the amplitude of the signal. It can be a voltage, it can be a current, and omega is the angular velocity, which is 50 Hz for AC currents in Bangladesh, and the quantity omega times t is the phase of the sinusoid at a particular time. Now, a phasor is basically a sinusoid represented as a vector in the polar coordinates. A phasor has two quantities, the magnitude and the phase. Now let's look at a simple analogy to see what a phasor looks like. On the right, we have a sinusoidal wave whose angular velocity is omega. On the left, there is a circle whose radius is the amplitude of the sinusoid, and this circle is in the polar coordinates. On the x-axis of the sinusoid is the phase of this sinusoid, and on the y-axis is the magnitude of the sinusoid at times t. So let's start moving along the sine wave. At time t1, the sinusoid is at point A. The phase of the sinusoid is theta 1, and it has a magnitude of this blue line. Now, if we draw a horizontal line from point A to the left circle, we get a vector denoted by this blue line, which has an angle of theta 1. Similarly, if we go farther along the sinusoid, and if we reach point B, then for point B, we get this purple vector in this polar coordinates, which has the angle theta 2, which is actually the phase angle of the sinusoid at point B. Similarly, for point C, we get this orange vector in this polar coordinates. So, which means a point on the sinusoid corresponds to a vector. A point on the sinusoid corresponds to a vector on the polar coordinates. Now, if we look closely, we will see that all the vectors have the same magnitudes. But their angle is indeed the phase of the sinusoid at a particular time. And as time increases, the vectors are moving in the counterclockwise direction. So it seems like there is a single vector which is just moving in the counterclockwise direction. And so here comes the concept of a phasor. So a phasor is a moving vector on the polar coordinates which represents the point on a sinusoid. As the point moves along the sinusoid, the phasor moves circularly counterclockwise, and at one full revolution, it completes one full cycle of the sinusoid. So now that we have understood the concept of a phasor, we will see how this concept is used to express currents and voltages in an AC circuit. Well, in AC circuits, let's denote a sinusoidal voltage as V equals Vm sine omega t plus phi, where Vm is the peak value of the voltage and phi is the initial phase angle. The phasor representation of V is a vector whose length is the peak value of the voltage, that means Vm, and its angle is the initial phase angle of the voltage. So any voltage or current can be represented as a phasor with its peak value and initial phase. Now let's take two examples. V1 equals 10 sine omega t plus 45 and V2 equals 5 sine omega t plus 90. So the angular velocity of the sinusoids are the same. They're the same. Now since there are two sinusoids, we need two phasors to represent each one of them. Here the V1, it has a length of 10 and its initial phase is 45 degrees, so it will be represented by this red vector, the red phasor. Okay, and for V2 it has a length of 5 since the peak value is 5, and its initial phase is 90 degrees, so its phasor angle will be 90 degrees. Okay, now notice that the angles have been put in the counterclockwise direction. If the initial phase is plus, then we put the angles in counterclockwise directions. Now, if we look at another example, the scenario is same except for the fact that the initial phase angles are negative. That's why they have been put in the negative in the clockwise orientation. So now that we have understood how to use phasors in AC circuits, we will see three cases in electrical circuits where phasor is really important. The first one is a phasor diagram in a resistive circuit. Well, here we have taken a voltage V equals 10 sine omega t plus phi, and from Ohm's law we can determine the current V over R. If you look closely, we will see that the initial phase of the voltage and current are identical. Now these two phasors, V and I, these two quantities, they only differ by their amplitudes. So if we put these two quantities in the phasor diagram, we will see that the V and I, they have the same phase angle. They have the same initial phase phi, but they have different amplitude. V has a higher amplitude and I has a lower amplitude. Okay. Then for a purely capacitive circuit, by manipulating the current voltage relationship, we get an expression for a current whose initial phase is actually 90 degree plus the initial phase of the voltage, whose initial phase is 90 degree plus the initial phase of the voltage, which means that the current in a capacitor is ahead of the voltage in phase by 90 degrees. And this is called, in electrical terms, this is called the current leads voltage by 90 degrees. And that's why we have put V here, and then we have put I 90 degree left of V, 90 degree counterclockwise of V. So from this manipulation, we find a pretty interesting finding is that in capacitive circuits, a current leads voltage. Okay. Similarly, for inductive circuit, if we manipulate this relationship, we get the expression of the voltage. And interestingly, here the initial phase angle of voltage is 90 degree plus the initial phase of the current. And that leads us to the conclusion that in an inductive circuit, voltage leads current or current lags voltage. So that's it. That was a short presentation on the phasor diagram in electrical circuits. And I think I haven't been able to discuss all the bits and pieces of phasor diagrams in this video, but nevertheless, thank you for listening. Thank you.